Good morning. Good morning. Today is January 13th. Today I'm going to comment on the last step of the process. Okay, basically what Engineer Isaac explained it to you in the previous two sessions was to have everything in order to get results. Okay, now if you have results, what can we do with those? That's what we try to explain today. Then I would like to do an evaluation of a student outcome. That's nothing to do with the grading of this class. It's just that we would like to know what you have, how advanced have you come into learning by yourself. Okay, so that's something related to the ABET process, okay, of accreditation. And at the end, I would like to do a check of your progress in the project, okay? And at the same time, the last few minutes, I would like to decide who is going to participate in the Naval Engineering Student Technical Sessions, okay? Engineer Isaac is loading in the Aula Virtual the material for today's session. So please download it from there, okay? If somebody can confirm me that he or she is able to download it, please. Did anybody was able to download the material that you're seeing here? Somebody?
It's not full screen.
It's not full screen yet. Okay, so let me swap. How about now?
Yes.
Okay, thanks. Isaac, did you load it in the Aula Virtual material?
Yes.
Okay.
I posted.
So students, please go to the Aula Virtual and download it from there, okay? Once somebody is able to do it, please let me know so I can continue with this explanation. Anybody?
Yes, it's out.
Anybody, people, please?
Yes, it's out.
So, okay, if somebody says that he or she is able, so everybody should do it. Okay, so I'm going to start now. I'm lost now. Where am I now? Shoot. Damn it. Okay, so this is what the Engineer Isaac explaining to you. These are basically all the steps in using finite elements. You can relate this process with the methodology that we explained at the beginning of the semester. Probably the terminology has changed a little bit, but you can recognize, for example, here, when you talk about meshing, remember, that means that we have a partition of the domain. When you say something about the definition of the supports, that means that you are imposing enough boundary conditions to have a unique solution. Okay, so all of this was explained in the previous sessions. Now, let's go to the last part, okay? After you get results, we need to do three things. First, we have to check convergence. Then we have to check those results. Do they make sense? And finally, this is the most interesting part, is after you do this checking, you analyze results. Okay, so we're going to say a little bit about these 3 points. Okay, first, checking convergence. Okay, please, this is not part of the analysis, basically, of the results. This is previously to do a analysis of results. Okay, it's like saying up to this point, you are not sure that the results are good enough. Okay, so remember, in chapter 1, we did. I'm trying to find what is my. Here it is. Okay, this is an example that we did in chapter 1. Okay, we hold a bar, and we analyze this using one element. Okay, and what we did was we impose here half of the weight. Then we did the same. Well, not the same. We analyzed the same system, the same bar with weight, but now we split it in 2 elements. Okay, here we applied a quarter of the weight. Here we applied half of the weight. Okay, and finally, in the homework, you had to do in the next step. And the next step was to analyze this, but using 4 elements. Okay, so you have to do this. This is the element, is the same one, but we split it in 4. There. So this is W over 8. This is W over 4, W over 4, and W over 4. Here, of course, you have some, and you have some there. And then, for example, we analyze the internal force. And the internal force exact is something like this. This is exact. It's like saying this is P as function of X star. Okay, and then we, in the same plot, we included the result from these partitions. So if you use partition 1, remember, we got something like this. So this is partition 1. If we use 2, then we got something like this and like that. And if we use 4, we got something like this, like this, like this, and like that. And you see that as you increase the number of elements, right, you see that you are getting close to it. Okay, and so this is something that we need to do. Okay, for example, let's suppose that we want to, for some reason, we want to determine the stress. Okay, I don't know, maybe in the central part of the bar. Let's suppose that we're interested in the stress here. So we want to analyze sigma x in this section, in the midship, in the mid part of the bar. Using these results, okay, you see that there is some differences as you go along with the calculation. So what we ask you to do is something like this. Okay, My suggestion is that you do this for not only one parameter, for several parameters. Now, I don't know. You can determine what parameters you are interested in. But here, for example, let's suppose that we are interested in a parameter, whatever, okay? And this is the exact solution. This is parameter star. See, as we say here, the exact solution is never known. And what we're obtaining is that with each one of these approximations, we are getting close to it, but we don't know because we don't know this value. But what we have to do is we can plot this using, for example, the number of elements, or we can do this with the dimension of the maximum size of one element, or you can select it. The first value, you obtain something like this, and then you go to the next value, and you see that there is some difference. The problem with 2 is that if you join them with a straight line, you don't know how close you are from here. So we need at least 3 partitions, okay? Let's suppose that the third partition gives you something like this. Then you immediately see that there is a curvature here. And the curvature here is showing you that you are getting flatter and flatter. And as you go on, you can assume that you are very close to the exact solution, even though this value, you never know. Okay, so this is the best way that we can do in order to check our results, our convergence. Okay, this is something that we have done in previous projects. Okay, always think about that. Okay, now in some cases, okay, this is very difficult to complete because of the large number of joints. What we can do in those cases is, for example, try to follow the recommendation from a classification society. Okay, for example, in some cases, you see that they recommend, for example, if you have something like this, okay? Okay, and you want to split this, partition this in plain elements, okay? And you know that if you apply a load down here, you're gonna have bending. And of course, the bending generates a compression on this side and a tension on this side. So you need to allow for this difference to develop in the model, right? So some classification societies, for example, they specify the maximum dimension here. Okay, and they mention, for example, that this number, in some cases, they say, for example, that the ratio between this dimension and this height cannot be larger than a certain value. Or can they tell you directly how much this maximum dimension could be? Okay, so these are 2 ways that you can check your convergence. Is there any questions about these, people? Any questions?
No, doctor.
No? Okay. So we have said plenty of this. I just want to insist. Now, okay, remember, this is not really analyzing the results. It's just previously. It's like saying, okay, I have to do this before I can start considering that my results are adequate. Okay, what's the next step? Okay, the next step is to check your results. Okay, and the minimum thing that you can do is you can say something about the sign of the response. Okay, in this case, for example, if you have something like the situation I'm showing here, of course, you need to say something that at least the deflection of this points downward. And of course, this is the end. So you need to check that the displacement, or in this case, for example, that you have 4 values of displacements. Okay, the largest is the one at the end. Makes sense. Because in this point, you support the load, all the load acting on the end. While if you calculate the displacement of this point here at 1/4 of the length, of course, that has to be smaller than this one. Okay. Similarly for the stresses. Okay. In some cases you have tension, in some cases you have compression. Those are things that you need to check in order to know that, to check your results. Okay. Now, this is probably something which is too easy, but you have to do it. Okay, at least do this. What else that we can do? What I suggest always is that you take your results, right, and compare them with simplified models. For example, last night, Engineer Marcelo was explaining the problem, okay, that they faced when they designed this in the first case. Okay, they had a mast and they were having some very high vibratory response, which did not allow the electronics to work correctly. Okay, in those cases, you can immediately see that this structure could be, in very simplified way, could be analyzed as a beam and bar. Okay, which is something that we can solve using solid mechanics. In other cases, you have, for example, many plates, flat parts. So you can compare those with the result from plates. Okay, so in the case of an elongated structure, I'm going to draw here something from last night, from the presentation from last night. So they have a ship, very nice ship. And up here, they have a mast. And this mast was vibrating. And we can model this immediately as what? See, we can see this as a beam clamped on its foundation. You see? We can analyze this using solid mechanics. This is X, this is Y. So we can take this and we can solve this quite easily. I know that the section, okay, of this mast is not uniform, okay, but we can consider this as a average section, and we can proceed in order to analyze, to get a result. And then what we can do is we have to compare. Okay, here we have to be careful, because if you have an axial load, for example, the weight of the elements that are here, since this is vertical and we have rotated this system, the weight is acting in the X direction for this case. So you could have an axial force, okay? And in this case, this axial force will generate, let's suppose that in this case, we have the weight pointing downwards. So in this case, P is going to be negative, right? Compression. So as a result of that, we can have this sigma X uniform. Okay. Now, in the same or a similar way, we can consider that there is also some, see here, I have some weight outside the vertical direction of the mast. And in that case, we're going to have some bending. And we immediately remember that if we get the bending moment, okay, mz, this bending moment will generate a normal stress distribution, which follows this expression. Okay, so for example, in this case, let's suppose that we have a deflection like this. Okay, yeah, because we're assuming that we have some weight in this part here. Okay, this is a weight. So it generates a deflection like that. So in this case, okay, the bending moment will be something like this in the positive phase. So here, the bending moment will generate a negative stress in the upper part of the section. So we're going to have something like this. We're going to have something like this. So this is compression, and this is tension. Okay, this is X, and this is Y. So we have two effects, right? So here we're going to have two effects, and in a simplified way that we're analyzing this, we can assume that this is, we can apply a superposition. So what we are going, I'm going to increase the size of the section, okay, to show the difference. Okay, so this is X and this is Y. So on this side here, on the upper side in my graph, I have compression and compression. And the other side, I have compression, but here I have tension. So as a result, we're going to have something like this. So we're going to have something like this. Okay, this is the mean. One side you add and the other side subtract. So this analysis that I'm developing here is for a beam. So we can do this in half an hour. And at the end, okay, if you do a final element analysis of this mast, okay, we're going to consider that. For example, let's suppose that we have something like this, and we split it like this using plate elements or flat elements. And each one of these is a joint. Okay. So if we calculate this, okay, of course, and on this side of the structure, we expect to have sigma in compression. So the normal stresses pointing downward will have to be negative. And these values we can compare with these values. And I put an interrogative sign saying that are they close? Do they have the same sign? Are they in the same range? This is a way that you can check. Something else on the other side, you can compare these with these values here. Okay, and then you can go on. For example, you can take the average of the two sides, right? And the average, probably you can compare with the value of the weight of the structure above this cut divided by the area of this cut. See, there are ways that you can check easily that these results make sense or not. Okay. Mr. Ordóñez, are you following me? Mr. Ordóñez, are you following me? Mr. Ordóñez? No? Mr. Valles, are you with me?
Yes, doctor. Good morning.
Mr. Ortega, are you with me?
Yes, doctor. Crystal clear.
Oh, okay. Mr. Mateo, are you here?
Yes, doctor.
Engineer Isaac, please remember, or Genesis, if I ask somebody and that person doesn't answer, please take them out of the session, okay? If he, for some reason, cannot answer, he has to come back, no problem. Let him in back again. But if it doesn't answer, that means that he's not here, okay? Okay, now, in some cases, for example, in this case that we analyzed last night, we can see this structure in a very simple way as a group of beams, okay? But in other cases, we have to consider as a group of plates, okay? And we have to do a similar comment as in the previous one. For example, if you have a group of plates forming the deck or the bottom or the side of a ship structure, okay? We could consider that the plate can support load on its plane. Now, for example, we have something like this. There, and we can support a force P of X. Okay, we could also support a force in the other direction. And if we divide that by the thickness, we get the stress, okay? Immediately you react and say, just a second, this is force, this has to be area in order to obtain stress, right? But we have to remember that when we studied plate theory, all the internal forces are expressed as per unit length. Do you remember that from previous semester? So this P of X, we call it force, but it really is force per unit length that we remember here. Okay? That means that if we make a cut here, okay, we make a cut, okay, we have a, let's suppose that this is positive, a sigma stress like this. So this is my sigma X uniform, okay? But in a similar way as in the case of there is somebody in the waiting room, Genesis. In the similar way as in the case of the beam, we could have also lateral loads, okay? And this lateral load can generate a bending, okay? So in this case, let me go back. This is not yet, okay? Jesus Christ. Okay, so we have something like the same plate, okay? But now the load is acting in this direction. Remember, this is what we call P of XY. And in this case, of course, we're going to generate, if we make a cut, an analysis here, we're going to have a bending moment. Here also, we have another bending moment in the other direction. We have to be careful because the directions are very important in this case. Okay, again, if we make a cut here and analyze the stresses on this cut, okay, we're going to have, this is the direction of the load, we're going to have something like this. So here I have compression. And on the lower side, I have tension. Okay, and this, of course, is the thickness. So this is sigma X because of bending. And let me insist that it depends on Z. Okay, now, if we analyze this using finite elements, right, we're going to have the results in every joint. So if we have these two effects, in general, if we do a linear analysis, we're going to have the combination of these two effects, okay? And as a result, let me increase the size of this drawing, okay? On the top, we're going to have the difference, and the lower part, we're going to have the summation of something like this. Let me change sign on the other side. So on one side, damn it. Jesus Christ. So something like this. So on the lower part, we're going to have tension, and it linearly changes. And the upper part, we're going to have compression. Okay, now here, if we call this is the top. I don't know, the pen is here. This is top, and below is the bottom, and this is the mid thickness. Damn it. Okay, so again, okay, we can compare the results at the top. Jesus Christ. The bottom, and at the mid part of the thickness. Okay. Now, when we do finite element analysis, okay, if we make a partition, okay, this, for example, could be an element. And in each one of the joints, we're going to have several results, okay? And we have to be careful because what result are we going to analyze, right? So before analyzing, this is something that we have to do. Okay, for example, if we have a plate supporting only lateral load, okay, if we plot the stresses at the mid portion, at the mid thickness, this value here, this has to be very small if there is no in-plane loading, right? On the other side, if you have basically no lateral load, only in-plane forces like Px or Py, in that case, the stress at the top and the stress at the bottom has to be very similar, okay? That means that basically the bending effect is very small. Okay, now, this is something that we need to remember. Now, in this case, how can we check our results? What we can do is we can estimate, for example, the bending response of a plate using results typical result, for example, from Timoshenko. Okay, let's suppose that we have it's my pointer here. Let's suppose that we have an structure composed by several. Okay, let's suppose that this is a girder, and this is an stiffener, right? Now let's suppose that we have pressure acting downwards, from downwards and up. I'm sorry, upwards. Okay, we can consider this rectangular piece of the bottom in a very simplified way as a clamped plate, okay? And we can analyze this in a way. Now, in finite elements, we're going to have the zillions of results. For example, this structure is going to be discretized. For example, let's suppose that I have one joint here, 2, 3, and 4, and so on. I'm not going to draw more. Okay, what we can do is we can take, for example, one joint here and one joint in the center. And we can check the results in these 2 points. And we can consider that this plate, okay, is a rectangular plate clamped on all edges. You can say, wait a minute, but the edges are not clamped. I know. You can tell him, for example, that the pressure is not uniform. It's not uniform. You can take an average. But the thing is that you have to check the level of the order of the response. So if you model that as a clamped plate, we can use, for example, this result from Timoshenko, and we can use the ratio, okay, B over A, get into one of these expressions, right? Get these values. These values you can evaluate here, for example, the deflection, okay? And also we can evaluate the bending moments, right? So remember that the bending moment is going to be very important in the direction of the smaller dimension. Okay, so in this case that I'm drawing here, this case, this dimension in this, you consider this as B. So this bending moment is going to be very important. Okay, in the central part, we're going to have this and that. And we always have to remember that in these cases, when we have rectangular plates, we are more interested in the direction of the smallest dimension. Okay, now, in the case of the deflection, okay, we have to be careful because if we have an structure like this one here, I'm going to draw something like this. And let's suppose we have loading downwards. Okay, I'm going to change color to draw the deformed situation. The problem is that the stiffeners can deform like this, like this, like that, and like that. And in here, the plate will also deform. The plate will deform like this. It will go downwards and will recuperate and go back again. And in the other direction, similarly. We have something like that, downwards and recuperate. Now, if we plot this in a profile, so this is the original. This is the deformation of the stiffeners. In here, we have the deflection of the plate. So we have something like this. So this deflection is the one that has to be compared with this value. Okay, so what we have to do is like considering the deflection of the borders, okay, which are the deflection of the stiffeners, and get the difference with the deflection at the central part of the plate. And that's the tertiary deformation that we can compare, for example, using Timoshenko's results. Okay. Is there any question, people? Any problem here? No?
Yes, doctor.
Yeah, go on.
Good morning. I have a question. What could be the percentage allowed between the result and the analytical and the
Jesus
ANSYS
Christ.
result?
Oh, man. That depends on the situation in general. If you're saying something about this, the problem here is that you never know this result. So, no, you cannot say the difference. Why not? Because you don't know P star. This value is something that you never know. If you knew this, then you don't need finite elements. That's a problem. Okay, so it's I guess it's a matter of experience. At the beginning, okay, if you doubt, what you have to do is you have to be certain that you are close to the correct one. And probably at the beginning, we will waste a lot of time with this. What do I mean by this? Let me change. Okay. For example, hopefully I will here. Let's suppose that we have a simple beam. We split it like this, then like this, then like this, and on. And you know that, for example, let's suppose that the deflection, the maximum deflection is here. Now, this value, this is the star. And this is the number of elements that we are using. This value we don't know. Okay, so we start here, we get a value, but we don't know how close or how far apart we are from this value. We do a second chance, a second calculation, then a third one, and we see that we have some curvature in this direction, showing that this slope is smaller than this one. So the change that you would expect here, as you get closer to the exact one, you don't know. So in this case, since you don't know how to evaluate this distance, this separation, probably we have to go one more step. And at the beginning, when, for example, let's suppose that we try to analyze a very strange structure. There is no experience. Probably my suggestion is go one more. So you recognize that the distance between this solution and this one here, this distance is very small. But still you're not sure. What do you have to do? Do one more. And check that you indeed are very, very horizontal. That means that you are very close to the exact solution. So as you get more and more experience, you will know that probably around here, that's enough. But at the beginning, since we have no experience in this type of structure, maybe we have to spend extra time and do extra analysis, even though we just want to check previous results. In some other cases, with some experience, probably you know that if you have a difference between these two partitions, that's enough. But that depends on the experience of the person who is analyzing. Okay.
Okay, doctor, I have another question. For example, when we finish the analyze the structure, we can change the structure to recommend another structural change in this whole part, or is just analyze the same or the original structure we get it.
You have to be clear what you want to do. You want to do analysis or you want to do design?
I would
You want
like
it-
to recommend the
Yeah, but in that case,
change the design of the structure.
yeah, but
For
in that
example,
case,
I did one reinforce in one part
yeah,
and
but
show the result.
the problem is this, okay? You have to be careful because when you analyze and recommend, let's suppose that you recommend an increase in thickness, okay? This increase in thickness is a little bit of design because you're changing the dimension of the structure. And we have to be careful because the person who hires you maybe is thinking that with this delta T is enough to take this problem and solve it. And you have to be certain that with this delta T, the loads will be producing adequate levels of stress. Okay, but yeah, it's a big difference between analysis and design. When you do analysis, you don't have to make any changes in the structure. When you design, yes. When you do design, they will ask you to give me the dimensions. See, the thickness, the height, the spacing, and all of this. That's design. So we have to be careful with this, okay? If somebody hires you to do a design, you have to have in your mind that this process will take you much more hours than this one here. And of course, that means that this costs more than this one. In the case of analysis, you're expected to say, be careful here or there, or in general, it will satisfy or not the requirements. In this case, you are expected to give me all these details so I can go on and construct safely. So the design includes analysis, not the other way. Mr. Jimenez?
Thank you, Doctor.
No problem. Anybody else, people? Any other question? Okay, we're going to go to a break here, and when we return, we're going to do a survey, okay, that allows us to evaluate one student outcome. We have to remember that those results from those survey are not going to be considered as part of the grade of this semester. Okay, this is just for us as a university to know how good we are in general in this, specifically in this outcome. Okay, so let's take a 5-minute break here.